Rolling is a special type of motion where an object possesses both rotational motion and translational motion. Rotational motion is motion where an object is spinning about some central axis, and translational motion is the motion of an object that moves from point A to point B. To consider an object that is rolling, let us investigate the tumbleweed, a plant endemic to the dullest and most boring places on Earth. Winds that blow across a prairie will cause these plants to roll across fields, roads, and other flat terrain. So, to investigate rolling, let's consider a tumbleweed rolling across a road. Now, we could ask the question, does a tumbleweed only rotate when it rolls across the road? Well, we said the answer to that is no. Let's consider what that would imply. If a tumbleweed were to only rotate, we could imagine that there might be some small insects located throughout the tumbleweed, and the further away an insect is from the center of the tumbleweed, the faster its velocity would be, because V equals R omega. However, the tumbleweed is actually going to be moving. The velocity of the insects in the tumbleweed will always be in a direction tangential to the rotation. In other words, the velocity of the insects is always going to be perpendicular to a line from the location of the insect to the center of the tumbleweed. The velocity, as we said, is given by V equals R omega. And if a tumbleweed were to only rotate, then the tumbleweed would just be sitting in the middle of the road spinning, and this is not rolling. Does a tumbleweed only possess translational motion? Well, the answer to that question also is no. If a tumbleweed only possessed translational motion, then the tumbleweed would just skid across the road. In that case, every point in the tumbleweed would have the exact same velocity. The tumbleweed is just moving across the road, not spinning at all. And this is not what rolling is. When a tumbleweed rolls, it both spins and it has translational motion. So if I were to say the velocity vectors from rotation look something like this, and the velocity vectors from translational motion look something like this, I could determine the velocity at every point in the tumbleweed by adding these vectors together. In that case, the velocity vectors across the tumbleweed would look something like this. Near the ground, where the tumbleweed is physically in contact with the ground, the velocity of an insect right here near the ground is going to be 0. But as you get further and further away from the ground, the velocity at these locations is going to increase. Rolling is essentially an object falling over itself, and because an object is a sphere or a circle, that object will be continuously falling over itself. We could ask what causes an object to roll in the first place. So let's look at these two types of motion separately, and we'll consider what forces might cause an object to roll. So let's assume that there is a wind blowing across the prairie, and this wind is pushing on the tumbleweed. Now, the tumbleweed is relatively small compared to the size of a giant air mass, so we could assume that the wind is pushing evenly across the tumbleweed at every location on the plant. So the wind is pushing evenly across the tumbleweed, so I expect the tumbleweed to feel that push, and as a result of this, it will have some translational velocity that looks something like this. Now, there is another force on the tumbleweed. The bottom of the tumbleweed is in contact with the ground. Therefore, there is going to be a force of static friction between the bottom of the tumbleweed and the ground. Think about a tire that is on a car that is driving down the road. The bottom of the tire is in contact with the ground, and you don't want that tire to slip. You want that tire to grip the ground. You don't want the tire to be moving while the car is in contact with the ground. There is a force of friction between the bottom of the plant and the ground, but there is no other force of friction between the plant and the ground because this is the only location where the plant is actually in contact with the ground. If I were to look at both of these forces, the bottom of the plant is not going to move, but the rest of the plant is free to move because There is a force of friction to the left on the tumbleweed, but there is a force of wind to the right on the tumbleweed. However, at other locations in the tumbleweed, there is only the force of wind. As a result of this, the tumbleweed will continuously be falling over itself. Later on in a lecture, we're going to see that this can be stated more eloquently as friction provides a torque on the tumbleweed that causes the tumbleweed to rotate. So, in this discussion, don't think of what we did here as a general formula. Think of this discussion as an example of how to analyze the physics of a rolling object. Now let's consider kinetic energy. When we presented the idea of kinetic energy back in chapter 6, we said kinetic energy is an energy of motion. In chapter 6, we considered the motion of an object that moves from one location to another. That's called translational motion. And we said kinetic energy is 1/2 mv squared. But let's consider an object that is rotating. So an object that is spinning but not changing its position. If I imagine the kinetic energy of a big object as the sum of the kinetic energy of all the atoms that make up that object, I could say atom 1 will have this much kinetic energy, atom 2 will have this much kinetic energy, atom 3 will have this much kinetic energy, and so on. And then I could say the total kinetic energy of the object is the kinetic energy of atom 1 plus the kinetic energy of atom 2, on and on. For an object that is rotating, even though the location of the macroscopic object is not changing, the atoms that make up that object each have their speed. Most of them have a non-zero speed, and hence I could infer that a rotating object will have some amount of kinetic energy associated with it, even if it's not changing its location. And this strongly suggests that there is a kinetic energy affiliated with rotation. Before we discuss the kinetic energy of rotation further, I first want to introduce the idea of moment of inertia. Moment of inertia is a property of a solid object that describes how the mass is distributed through that body. If you think of two very heavy masses that are connected by a bar, you could have something like the picture on the left, or you could have something like the picture on the right. In both of these pictures, the objects have the same mass. There are two large spherical masses connected by a bar. But the mass is distributed differently in these two objects. In the picture on the left, the mass is further out towards the ends of the bar, while in the picture on the right, the masses are close to the center of the bar. Now, as a thought experiment, let's consider that these objects are both spinning around. They both have the same angular velocity, omega. Think about it, ask yourself, which of these objects would be easier to bring to a stop and why? So pause the video, think about this question, and come back with an answer. The object on the right will be easier to bring to a stop. So if I imagine I am spinning something, if I put the masses far away from the center of rotation, it will be difficult to bring to a stop. If I bring the mass in towards the center of rotation, this object will be easier to bring to a stop. That is what my intuition tells me, but why might this be? Well, another way of thinking about moment of inertia is you could imagine how easy or difficult is it to cause that object to gain an angular acceleration. And think about this statement in the context of our definition of mass from chapter 4 when we talked about forces. When we learned about forces and Newton's second law, we said that you could imagine mass as an object's inherent resistance to acceleration. In much the same way, you could think of moment of inertia as an object's inherent resistance to an angular acceleration. In its most general form for this course, the moment of inertia of an object could be written as I total equals the sum of mr squared. On the left-hand side of this equation, capital I is the moment of inertia of an object. On the right-hand side of this equation, we see a summation. So, in principle, if I have an object that is made up of Avogadro's number of particles, I would need to add up mr squared for every particle that makes up that object. So that would imply I need to add Avogadro's number of terms together. In practice, that is not going to be very practical at all. Often what we do is if we take a macroscopic object, we could often approximate that object as the sum of several particles added together. So if I take an object and to a good approximation, I could treat that object as 3 or 4 point particles, then I would only have 3 or 4 terms in this summation to add together. When I perform this summation is taken over each particle that makes up my object. So the first term in my summation would be the mass of particle 1 times the distance squared from particle 1 to the center of rotation. The second term in my summation would be the mass of particle 2 times the distance squared from particle 2 to the center of rotation. The third term in my summation would be the mass of particle 3 times the distance squared from particle 3 to the center of rotation. And I add that up for each particle that makes up my object. So this sum is taken over every particle that makes up my object, but very often in a real-world scenario, we'll be able to approximate objects as a few particles, not as Avogadro's number of particles. Now, in principle, we do not need the origin, where r equals 0, to coincide with the axis of rotation. However, in this course, it is very highly recommended that you do make that choice. The physics will still work out if you choose the axis of rotation to be located not at the origin, where r equals 0, but you're going to end up making your life a lot harder, and I highly recommend you don't do that. Now, hypothetically, if the mass of an object is smoothly distributed over some simple shape or volume, then you could turn this sum into an integral and integrate over the volume of that shape to find the moment of inertia of a solid object, like a book or a propeller blade. However, this is not a calculus-based physics course, so you could just go to the table in page 220 of the textbook and look up the moment of inertia for some simple shapes. Somebody has already calculated that for you. So now we will talk about the kinetic energy of rotation. We now have two types of kinetic energy. There is a kinetic energy of translation that is given by 1/2 mv squared. The kinetic energy of translation is the exact same kinetic energy that you learned about back in chapter 6. We only added the subscript translation to differentiate between the two types of kinetic energy, but everything we said about the kinetic energy in chapter 6 still applies to kinetic energy of translation. They are the same quantity. There is also now a kinetic energy of rotation. And the kinetic energy of rotation of an object is given as 1/2 I omega squared. If you look at these two equations for kinetic energy, notice how closely they resemble each other. In both equations, we have a 1/2, we have a term that describes a resistance to acceleration, we have a term that describes a resistance to angular acceleration. We have a speed squared, we have an angular speed squared. So when I said previously that for pretty much all the physical quantities we learned about, we're going to have a rotational analog, this is an example of what I meant. Now, an object could potentially be both moving and rotating. An object that is both moving and rotating will have a kinetic energy of translation and a kinetic energy of rotation. And to find the total kinetic energy of the object, I just add up these two types of kinetic energy. So if an object is spinning around as it is moving, you can imagine the Earth is spinning as it orbits the sun, then the Earth will have a kinetic energy of rotation as the Earth spins around its axis, and the Earth will have a kinetic energy of translation as the Earth moves around in its orbit. So you will have a 1/2 mv squared and a 1/2 I omega square. When we first introduced the concept of work at the very beginning of chapter 6, we said you could imagine work as energy given to an object as a result of pushing on the object with a force. And we proved the work kinetic energy theorem. The total work done on an object is equal to the change in the object's kinetic energy. When we are looking at work in the context of rotational motion, the work kinetic energy theorem still applies. We still have the total work done on an object is equal to the object's change in kinetic energy. However, now we have two types of kinetic energy. So I would say the total final kinetic energy is the final kinetic energy of translation plus the final kinetic energy of rotation. And the total initial kinetic energy is the initial kinetic energy of translation plus the initial kinetic energy of rotation. But the important thing to take away from this slide is that the work kinetic energy theorem still applies. It is unchanged, even though now we have two types of kinetic energy to consider. If we push on an object, we might cause that object to change its speed. That would cause it to gain or lose translational kinetic energy. We might cause that object to change its rate of rotation. It might spin faster or it might slow down its rate of spin. That would be like saying it changed its rotational kinetic energy, or in the act of pushing on an object, we might cause both to happen.